So, the objective of this lecture 9, I will break in 2 lectures, 9A and 9B, which I want finally to obtain the Hamiltonian as a constant of motion. See, constant of motion of Hamilton. See. Now let's start from lecture 9A. I will apply as a second example the harmonic oscillator, in which H is a function of Q of t and P of t. Q are generalized coordinates, and P are the momentum. Now you can see here that T is not explicitly involved. This is for autonomous system. Now let's start from Newton's second law to reach the Hamiltonian, and then on 9B I will find the constant of motion, harmonic constant of motion, the trajectory of the Hamilton. Now let's dedicate this 9A, the Newton's second law, to the Hamilton. Okay? Now we start with the physical settings. First, one particle of mass m under the restoring force of a spring. This is what we call a simple harmonic oscillator. So again, I will emphasize that no explicit time-dependent forces. You see, I will start from step 1, Newton's second law. Mass times acceleration is equal to the sum, the resultant of all the force that act on this element, okay, on this element or this body of mass m. Now there is only one, you see, what you call the restoring force of the spring. So for the harmonic oscillator, the restoring force is minus Q. Q is the spring constant, and times the generalized coordinate. You see, this is the displacement. Okay, when you talk about the spring, we call this generalized coordinate as the displacement. So K is the spring constant. Thus, the Newton's second law leads to mq double dot, which acceleration is minus K times the displacement, which is the generalized coordinate G. So then I can play with this equality over here, and leads to the acceleration plus K over mq is equal to 0. Then I call equation 1. Attention for this mark over here. Okay, the sign here is just over there. So from here we jump to there. So this over here, this 1, is the standard differential equation for simple harmonic motion. By inspection, attention, you will not derive this relation here. There is no derivation for it. It is by inspection you can represent the displacement Q of t as a sinusoidal functions. A cosine omega t plus phi. Phi is the phase, okay, where the solution is a sinusoidal, okay, the solution of what? Of this differential equation over here. So this is the solution. Now, just you take the first derivative, okay? Then the q dot is minus because derivative of cosine is minus sine. See, this is the omega, okay? So again, the second derivative, this is equal to minus omega square A cosine of omega t plus phi. You can see clearly that cosine, you see, this term over here, there is no unit, okay? So omega has the unit of 1 over time, which is frequency, in general in hertz. So then I repeat, you see how it's clear that this over here is just this over here, you see? So the second derivative I can represent to minus omega squared q of t, where omega is the natural angular frequency, as I said. So q, the acceleration plus omega squared q of t is equal to 0. Attention now, I compare, you see, I compare the solution, and this leads, I can write that omega squared is k of m. So I compare the solution on this equation over here. So I compare with this. So this there is just omega squared. See? It's quite clear. So the acceleration plus omega squared q of t is equal to 0. This is equation 3. You see? Because I substitute equation 2 into equation 1. Equation 2 is just this one, and equation 1 is this one. You just substitute, see? Then leads to this simple equation, second order differential equation, number 3. So step 2, attention now, this is step 1. Now this is step 2. Then I will find the Lagrangian. Okay, attention now. The Lagrangian leads to the Hamiltonian using what? Use the Legendre transformation. Go there, that the derivation is clear, okay, in previous videos over there. So then I can write another point that's very, very, very important is this. Do you see the Lagrangian function of generalized and the velocity q dot? This is the velocity q dot. So this is kinetic energy function only of the velocity minus the potential energy, okay? This is joules in this case. So V of Q, you see? Remember, the potential energy is force dot displacement. That's a work due to this restoring force over here. That's why this leads to Q squared, because F of Q is minus Q, KQ times Q, this is KQ squared. So this is a kinetic energy minus KQ squared, as I said. So I just write the Lagrangian here. The right hand side now is minus plus 1/2 m cube dot squared, the velocity squared is kinetic energy minus the potential energy. Now this is minus KQ squared. I just wrote over there. See, this is a potential energy. That's exactly from there. So, as I said, I derived this before, and I define, you see, the momentum P as the partial derivative of Lagrange respect to the velocity. So I just substitute L over here. You see, this is L, okay? Now that's it's clear, okay, that this is L. So I substitute L over here, you see, and then I take derivative. Attention now, this term over here is not function of Q dot. So it disappears when I take the derivative of this, the potential energy. But the kinetic energy, you have derivative of Q dot and Q dot square. So use the simple derivative, then this you lead to m Q dot. You see, just take the derivative, because derivative respect Q dot or this term here is 0. Then now I can get Q dot, the green one, as P over M. Okay? Don't forget that P is the momentum. See? Momentum is m times v. See? Now, this is from here, this leads to PQ dot is P squared of m, which is quite clear because if I multiply both sides by P, PQ dot is P squared divided by m, which is here. So L in terms of momentum, P is, attention for this signal here, okay, this goes over there. So L, QQ dot, I want to represent L in terms of Q and P. Why? Because I'm walking toward the Hamiltonian. Hamiltonian only depends of Q and P, not Q dot. So this leads to LQP is minus, just substitute, quite clear, okay? I substitute this Q dot over here on L, you see? So this is 1/2 m, P over m squared minus, this over here is this potential energy. This is kinetic energy, potential energy, okay? So this P squared divided by m squared, I can cancel this m, so this I come up, leads to P squared over 2m, and this minus 1/2 of m omega squared Q squared. Now attention now, recall from the Legendre transformation, you see how we obtain throughout the Legendre transformation how to obtain the Hamiltonian. So we will define Hamiltonian as PQ dot minus L, you see? Then PQ dot is MQ